Okay, away we go. Good morning, everyone. Are there any questions to begin with? Katie? Yeah, so I'm going to repeat your question because you're not near your microphone. For the thing that's due tonight, is it okay if we do not use the online mock-up tool? Yes, that's fine. It's just a tool. It's useful, but there's plenty of other ways to accomplish the same task. So, yeah, that's fine. Yeah, drawings are fine. Absolutely. If you're quicker with a sketchbook, feel free. Other questions? All right, I have a question. Some of you have already submitted something. How does the group thing work in D2L? Because I spent a whole bunch of time trying to enter the groups correctly, and I can't tell from the faculty view if it worked. So, has anyone in this room submitted something yet? At least a draft. How did it work? Just like a normal Dropbox? Could you tell who was in your group? Okay, can I ask you to have your partner go look at D2L and see what they see, and make sure that you can see the thing that the both of you are submitting, right? Can you check for me that that's the way it works? That's how it's supposed to work, but I've never, the group feature is new to this edition of D2L, and I have not used it, so I just want to make sure it does what it's supposed to.
I have a submission.
Okay, so you can see the thing that he submitted. All right. Yeah, Liam.
Go to where it says communication and you click on groups, it'll show you your group number, and
Okay.
then there's like a number for the members. If you click on that, it'll tell you who's in your group.
Okay, so supposedly these are self-enrolling groups, but I put in initially what I knew about the groups to begin with. So do you see anything in the interface for I want to change my group or I want to join a group that already exists? Is that there? Because there are some loose students that I don't know which group they're in, and so I want to know how that looks to you for turning something in. Does anybody know? All right, well, give it a try and let me know what you figure out, because there's a bunch of groups that are in the system that don't have any students in them yet. And those are there for the students that I don't have information about what team they're on. And so I'm hoping that it is a system that, because it's labeled self-enrollment, that there's some mechanism for you to assert to D2L, this is the person that's in my group with me. All right, if that is not the case, let me know and we'll figure it out. But I'm pretty sure you can submit something to the Dropbox either way, right? It just might not know that you're partnered with someone, and we'll straighten it out later. Okay. Make sure everybody's name is at the top of the document that you submit to the Dropbox, right? That would be a safe thing to do under any circumstances. Berlin West was wondering that because we have only 4 people in the class here, if we could just have 1 group of 4 instead of 2 groups of 2. Yeah, if you guys are comfortable with that, that's fine, West. Any other questions about the grouping or the submission or any of that stuff from the group? All right. I have some things I want to say about grading, which are sort of in the general question category, but also there's the questions from the cards from Monday, and I didn't get a chance to answer those online, so I'll just answer those now. One question was, how would you suggest memorizing the code for the exam, rewriting it over and over again? So we finished off the binary tree code, and I said I expect you to be familiar with this for the exam. I would not suggest that you memorize code for a binary search tree. That is not my style to ask you questions that require you to regurgitate memorized code. What I'm hoping is that you will understand the particular implementation of binary search tree that the textbook and I have gone through, and could answer questions about using it, or if I gave you some functions, some function headers for, say, a different variation on that implementation, that you could reason through what should happen and be able to write some code for that, right? Clearly, given that it took me 4 lectures to present all the code for the binary search tree, I would not expect you to write a binary search tree from scratch on a final exam, right? That would be longer than the 2-hour window we have for the final exam. Moreover, it's just not useful to me to ask you to regurgitate code. Right? So the goal should be to study that code that we spent time on in class. Go back and look at the recordings of the lectures if you like. Read the chapter where they explain it at length. Make sure that you understand why that code, what it does. That's not the only way to build a binary search tree. It's a good way, but the important part is understanding how a binary search tree works conceptually, and what are the Java tricks that you need to know to be able to implement one successfully that's going to be useful as a generic tool. All right? Are child nodes designated to be the left or right of the parent node? And how would this be noted in the code? So I think that question goes back to, we spent a long time implementing this, right? And actually we did the binary search tree node way back in the first day, where we pointed out that there's two link fields and one's called left and one's called right. And so that's how the parent knows which child is left or right. But does the child know which child it is of a parent? If I'm looking at a binary search tree node, can that node tell me whether it is the left or right child of a parent? Not in the implementation that we wrote up, because it's only singly linked, right? The children do not have links back to their parents. The parents have forward links to the children, which is why all the recursive operations we implemented, we always started up at the root of the tree and then recursed down, right? Could we implement a fancier binary search tree where it was doubly linked and every child had information about who its parent was? Yes, you could totally build that. We did not. We didn't happen to need that information at any point, but there's certainly other implementations of binary trees where it would be super useful to be able to, if you have a child node, figure out who is the parent and whether you're the left child or the right child of that parent. But that would require some additional code and some additional work that we didn't bother doing for our example. All right, so good question. But the answer is the child does not know whether they are the left child or the right child of a parent. Only the parent knows in the implementation that we did with the textbook. All right. Are we going over graphical user interfaces on Wednesday, or are we expected to learn it on our own? Neither. I'm planning on going over it on Friday, but I'm not expecting it to totally learn it on your own. All right. And why is it called a binary search tree? Why not just a binary tree? That's a great question. So there is such a thing as a binary tree. The binary search tree is a very specific example of a binary tree. And what makes it a binary search tree is, well, what does make it a binary search tree? I'll put that question back to the class. What made the binary tree that we spent 4 lectures working on a binary search tree instead of just a plain old binary tree? Colin?
How we ordered the elements in it?
Yeah, it was that ordering rule that we put up on the slides the very first day we started implementing all the code, right? This ordering that if the payload in a node is less than or equal to the node that I'm on, it has to go to the left, which is not the only binary search tree rule we could have. We could rearrange that rule in several different ways, but that's the one we used for that particular implementation. And the fact that there was a global ordering on the nodes is what makes it a binary search tree. Because if I'm looking for a particular node, that rule means I have a specific algorithm to follow to find whether it's in the tree. And if I get to the bottom and I don't find it, I don't have to look around in the tree and see if it's somewhere else, because the rule tells me there's really only one route that I could take to get to a particular piece of information in the binary search tree. So not only do I get that nice log n efficient traversal for finding my way to an element, but if I follow that path and I get there and the thing I'm looking for isn't there, I know it's not in this binary search tree. And that's not true of general binary trees. General binary trees where the nodes could be in all different kinds of orders, there's lots of other algorithms that are still very efficient, but they're not as efficient as in a binary search tree where I have this really strict ordering of elements. Make sense? And in fact, that's a nice segue into what I'm going to finish off today from our chapter, which is other kinds of tree structures other than just the binary search tree. All right? I want to say a couple words about grades, because I've gotten a lot of questions in the past couple days about grades. So first of all, I want to make it clear that project 1, 2, 3, and 6 have been graded. And you should see grades for those in D2L, and you should have received some kind of response from the human TA with graded output, right? So a score and something that indicates why you have that score, all right? Projects 4 and 5 and 7 are not yet graded. They are still in progress. 7 is the one we just turned in, right? And 4 and 5 were the percolation and the percolation variations. So actually, our human TA didn't realize there was 2 of those and is waiting for me to provide the final test data for project 5. And so she also didn't start on project 4 because actually one of you told her that it was just an extension of the other one. So she was confused that there was actually a project 4. To wit, you may have noticed on Monday, a bunch of grades went out that were labeled project 5, but in fact, they were your project 6 assignments. All right, and then like an hour later, it went out corrected. It said project 6 up at the top. All right, but it was labeled project 5 because the TA and I were not on the same page for which projects were which, and also some people didn't get one of the broken email, so it was broken in 2 ways. But later that afternoon, everybody's project 6 score should have gone out. All right, so if you look in D2L and you see I have a 0 for project 4. No, project 4 is not graded yet. Some of the columns are in there because we're adding them as we start processing the grades, but they're not filled out yet. All right, so I've gotten a bunch of questions of the form, everybody else has their grade for project X, why do I have a 0? And in about half the cases, it turned out they were talking about a project that wasn't graded yet. And so the base assertion that everybody else had a grade for it, that was wrong. All right, so there's a lot of rumors going around that, everybody else has grades for this, and I don't. If you have not received human graded output from something, then you should not expect to see a grade in the grade book yet. All right? However, there are some examples of projects that have been graded where people did not get their graded output back. And so sometimes those were actually things that we had to track down why someone didn't get a graded response. So sometimes it's turning out people are putting the wrong email address in the TA-bot mail-to tag. They'll have like a typo in their email address, and TA-bot very obligingly, after the human grades the system, we have a script that we run that mails the results out back to everybody because we're not going to sit there and manually mail 65 assignments back to students, right? And if you have put a typo in your email address in that TA-bot mail-to tag, it will dutifully try to mail that to a non-existent mail address. And sometimes that bounces back in a way that we can see it, but sometimes it doesn't. So some mail got lost, and we need to track those down and resend them to the correct email address. Some students did not put a mail-to tag or misspelled the mail-to tag, in which case the default behavior is Mailbot sends that to their MSCS department mail account, the one that you have to go to the MSCS department webpage and click on that webmail link to read it. And that's just not a mail account that most of you even bother to check. And that's why it's so important to put the TA-bot mail-to tag in your homework so it goes to the right place. All right? So there's a couple of weird cases like that that I've been tracking down this week. Again, the general rule is if you see a non-zero grade in the grade book, or you really do know that everybody else has gotten a grade for a particular project and you have not, do let us know that, all right? Because it could be that something's lost in the work. It's a big class. There's 60+ students, right? It's easy for us to lose one here and there where we didn't notice that it got mailed to a non-existent address, or a file wasn't in the right place and therefore didn't get sent out in the mail at all. I found that in a couple places as well. All right? We do have some filing errors that take place. But all your work is preserved. Anything that you submitted through the turn-in system, that is on a backed up system that we can backtrack and we can find it if it's in there. So you just got to let us know if something's missing. All right? But there definitely should not be mystery grades in D2L where you have a score and you did not get a human graded thing back that tells you why you have that score. All right? So if you are in that situation, please come talk to the TA or talk to me, and we'll figure out what's going on there. Okay? Any questions about how we're grading homework or what you should see or any of that stuff? So far, so good? Okay, excellent. Let's see, did I hit all of my talking points? Yes, looks like. Okay, good deal. So let's finish up on our binary trees. So we finished off our code, more or less, for remove. That was the last major method that was of interest for our implementation of the book's binary search tree. Okay, come on. Yes, present the desktop. Go. Kind of working. Good deal. So what more do we need to know about binary trees? Well, first of all, there's a whole bunch of other things besides binary search trees. But no, you know, I'll come back to that. Let's talk about balance first. So a really important part of the reason that we went through all that code that we worked on for the past 4 classes is because binary search trees are such a great option for organizing sorted data. And the reason for that is the efficiency of being able to retrieve data from them, right? So, you know, we're interested in the big O of various methods. And so what was the method for retrieving an item from the binary search tree? What was it called? Do you remember? I think we did that one last week, Wednesday. Not a magical name, but, you know, should ring a bell. I've got a thing, and I want to know if it's in the binary search tree. I call the method find, right? So your textbook is really consistent about calling that, don't capitalize that, about calling that find. So what is the big O of my find operation on a binary search tree? I already gave kind of a partial answer like 5 minutes ago, but that's not the whole story. And half of you weren't paying attention anyway. So what is the big O of find? So first of all, what is the n in this case? What is the n I am judging this against?
The number of items in the tree.
The total number of items in the tree. Now we need to be careful here because in some kinds of tree implementations, we only care about the leaf nodes down at the bottom, right? But in our binary search tree, items aren't just at the leaves, right? They can be in any of the internal nodes and they could be at the root, right? So our n here is the total number of items in the tree. As it turns out, if you have a binary tree and you only care about the leaves can be at most half of the total n, right? And so it turns out it works out to be the same big O operations. But ignore that bit, right? So n is the total number of items. So when I'm trying to find a specific item, in the worst case, how many links do I need to follow to find that item? N, right? Because we've got some really nasty cases that we could inadvertently get, where if I'm not careful, my binary search tree could be severely out of balance. And I've got a root node up here, and I just keep going off. And I could even, you know, zigzag a little bit, doesn't matter. But if each node only has one child, dot, 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 then I lose all the efficiency of the binary search tree, because suddenly I just have a fancy linear linked list, right? So I need to be really careful about how I construct my binary search tree if I'm going to count on that efficiency. Because in the worst case, find is worst case big O of n. And that's not super good. That's not worth all the extra effort we put into building a binary search tree if we get that case. What we want is the more typical case, right? So the average case we're hoping is, well, the average case, we want the tree to be bushy, right? We want to have nodes going down both sides and have this tree be relatively balanced, right? So what's my big O then? If I have a nice balanced tree, log of n. Now careful, not n log n. We've talked about n log n a bunch of times, but this is not n times log n. This is just log n, right? Because log n is the maximum height of a balanced tree, right? If I've got 1,000 nodes in my binary search tree, I can't have more than 10 levels in the tree, right? And that's just because of the powers of 2, the way it works, right? I'm doubling the number of nodes I can have at each level. So 2 to the 10th power is 1,024. So I need to have at least 1,024 nodes. I need to have more than that to have an 11th level on a balanced binary tree, right? So a lot depends upon my notion of balanced here. In our average case, this is going to be log 2 of n with the 2 subscript. Is there a shortcut for that? Can I do that? No, totally not. Where's subscript? Where's the thing? Control plus? No. Control equals? Are you guys just guessing? There we go. Control equals. Thank you. All right. So does this difference matter? The difference between big O of n and big O log 2 of n? Well, if I'm talking about 1,000,000 items in my tree, it's huge, right? If it's big O of 1,000,000, that's 1,000,000 operations. If each operation takes a second, that's a long time. But if I have log of 1,000,000, log base 2 of 1,000,000, that's 20, right? That's 20 hops, 20 seconds versus 1,000,000 seconds. So it doesn't matter when we're talking about small numbers. But when we start talking about big numbers, big databases with millions or billions of items, it becomes really important that we have log n search time for being able to find something in our tree, right? So balanced binary search trees are far more efficient than random/unbalanced trees. How about other common operations that we want to do with our binary search tree? Let's say we need to add a new item. Oh, fine, just capitalize it. I don't care. How expensive is it for us to add an item to a binary search tree? In the worst case, if I've got one of these big, long, unbalanced linked list-like trees, I might have to go all the way into that list, right? So big O of n. In the average case, if I have a nice balanced binary search tree, I at most have to go log n levels down to find the place that I need to insert an item, right? So add has this same property. The balance of the tree really impacts the efficiency of my operation. The same is going to go for remove. The same is going to go for all of the other common operations that I want to perform on this data structure as a collection class. So everything comes down to whether my binary search tree is balanced, right? So this is the same thing. No, false. I get for trying to use hotkeys. So the big question is, how do we maintain balance in a binary search tree? That's the question of the hour. The add method that we've built so far just finds the correct place for the node and doesn't guarantee anything about the balance of the tree. And so if we add our items in order into the binary search tree, what are we going to get? If I start with an empty binary search tree and I add into it one at a time the elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What's my binary search tree going to look like? Yeah, exactly that pathological example I was talking about, right? The 1 will be at the root, and the 2 will be its right child, and the 3 will be its right child, and it's just going to zoom down like a linear linked list. So binary search trees actually perform really poorly when we're trying to build them, and the elements that we want to add are already partially sorted, right? That's actually worse than just randomizing them and throwing them in, where we're bound to get a somewhat balanced tree under normal conditions. Right? But if we want to actually build it into this data structure, because it's so important for this efficiency, how do we maintain balance in the binary search tree? What can we do? What kind of additional code can we write to make sure that this is going to happen? Or that after we've added a bunch of items, we can build a balanced version of the tree? Shouldn't be super hard, because actually there's like a whole section on the textbook on this, which hopefully you read last week. But trying to see what you remember. Joseph, go ahead.
Like kind of a sorter method that would go through the items and sort them in order and then categorize them.
Categorize them how?
Like I forget the name of the order, but however the search tree is.
You're saying you want to insert the items in the correct order so it builds the balanced search tree, right? Okay, so if I've got a set of items that I want to insert, let's go with the numbers. 1, 2, 3, 4, 5, 6, 7, 8, and 9. I want to build a balanced binary search tree without any special code. I want to use the add method that we've already built. What's the order in which I need to put these elements in to get the tree to turn out to be balanced? Take a minute, consult with an elbow partner next to you, work out what is the order that I need to insert these, or an order that I need to insert these to get a balanced tree. All right, what do we got? Alex?
We said just like find the median, like put them in order, find the median value, like put that one in, and then find the median value of like each chunk, and then keep going down until you have it.
That sounds suspiciously like the same mechanism we do for a binary search of a linear array, doesn't it? Yeah. So what's special about the median? Why does that one need to go in first? Michael?
The median has to become our root so that each side of the tree maintains the same size.
Yeah, even if we don't know yet what the shape of the left side and the right side have to look like, the ordering of elements tells us that the middle element has to be in the root, because we expect half the items in the tree to go to the left and the other half to go to the right. So if we build the root first, then we have to find that middle element. So there's actually a bunch of different balanced search trees that we could construct with this particular set of numbers. That didn't work out very well. Let's try this. But it's hard to make this tree balanced if we aren't starting with the 5 up here at the top, right? Because we need 4 children on the left and 4 children on the right. Okay, so how many of you concluded we needed to start with the 5? Okay, good. So broad acceptance of that. What do we need to put in next? Is there one answer? No, we have some choices here. There's a variety of ways this could work out where we're going to get a reasonably balanced tree when we're done. All right? I can see 4 possible answers to my question. What do we insert next in order to get a balanced binary search tree? Who wants to give me one? Colin. 3 is a good answer. Who wants to give me another one? Alex.
7.
7 is a good answer. I like that one. Wants to give me another one? Jake?
8.
8 is also okay. So it turns out I can have the next child down on the right here be 7 or 8, right? So if this node has the 7 in it, then the 6 will go here, right? And I'll have the 8 and the 9 hanging off here. It's not totally balanced, but it can't be because I have 4 nodes, right? Or, backspace, 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 I could end up with the 9 here and the 8 over here, right? That's not unbalanced given the numbers that we're working with, right? But I could also end up not with the 7 up there at all. This could be the 8 that goes here, right? In which case the 9 is going to end up over here. And on this side, I can have either the 7 here and the 6 here, right? That's going to be legit. Or I could end up with the 6 here and the 7 here. All right, so I've got 4 choices for how to build the right subtree here. So it doesn't really matter whether I put 7 or 8 in next, but 7 or 8 needs to come before 6 and 9 for sure, right? And if I had an odd number of elements on the right-hand side here, instead of 4 elements on the right-hand side, then I'd have a for sure answer, right? I'd have a middle element that needed to go there. If I was going 1 through 10 instead, then for sure I'd want the 8 here. See that? All right, so there's a variety of ways we can build this, not just one answer, but for sure we've got to have the 2 or the 3 as the left child and the 7 or the 8 as the right child, and then we can build out the rest of it accordingly. Right? Same for the left child here. There's 4 different variations for how that could go. That's still going to be reasonably balanced. See that? Okay, so the structure of the tree mimics the order in which we insert the data into the tree if we use our traditional add that we just finished writing last time, right? So do we then see a procedure maybe for taking an existing binary search tree where we've already added all of the elements and we know it's out of balance? Can we take that binary search tree and transform it into a balanced binary search tree? Let me put that in a different way. If I give you a binary search tree that's perhaps unbalanced, but has all the elements in it already, do you know how to build the balanced search tree? Is there an algorithm for this that will get you the right answer every time, or a right answer every time? Yes. Yes, there is. What is that algorithm? Again, take a minute, consult with a partner. I give you a binary search tree. You know that it's unbalanced, but it's got all the elements in it. What's the code you're going to write to take that binary search tree as input and to produce as output a new balanced binary search tree that has all the same elements in it? Talk amongst yourselves. Take a minute. It's okay to use another data structure. All right, who's got an algorithm for me? Don't be shy. What do you got? Katie. What's that? The binary search algorithm. On what? That's not enough detail for me to understand how to do it yet. Alan?
So, I would go through each element in the tree that was given and put them in a list that's sorted.
So what you're saying there sounds like a traversal to me. Which one of the 3 traversals do we need to do what you're talking about? Anybody? I want to get all the elements back out of this binary search tree in order. Which traversal do I need? Of my 3 choices of traversal. The in order traversal. When I do the in order traversal, it gives me all the nodes in order? Is that possible? Yes, in fact, that's why we call it that, right? If I do the in order traversal of the existing binary search tree and keep track of all the elements as they come out, I will get the list of all the elements in order, right? What should I do with those elements? Immediately insert them into another binary search tree? No, that will build the worst possible binary search tree, right? I need to store all of them. We could use an array, or we could use, a list, but in some flat data structure, because what do I need to do next? Alan?
So do like a binary on it, and then each element that it hits, return it and put it into the new tree.
Right. The part of the binary search that Katie was talking about, right? By which we mean identify the middle element or a middle element if there's a tie, insert that one, and then recursively follow the same procedure on the 2 subhalves that are left, right? And if I recurse down, and I could even use a queue data structure and take the things that are in my array and insert them into a queue in the proper order that I need to rebuild the binary search tree, right? And I get all the same elements, but I have them now in the order that they need to be inserted in order to make the tree. And if I build a brand new binary search tree, inserting those elements in the correct order, I'll get a nice, beautiful, balanced tree. All right? Beautiful. Everybody understand how that works? Does that seem like a lot of work to get a balanced binary search tree? Yeah, kind of-ish, right? And it assumes that, well, okay, let me put it to you this way. Is this a good algorithm if I'm not done building my binary search tree yet? No, you definitely do not want to have to do this every single time somebody inserts a new thing, right? Insert it in, and then do an entire in-order traversal, build a whole list, and then start recursively building a brand new tree to do that, right? That's going to be horribly inefficient. While algorithmically correct, it will give me the correct answer. I would have a horrible data structure on my hands, right? Can we improve upon that? Is there a way we can think about balancing our tree at the time that we insert a new node into it, when we add a new node? Can we structure our binary search tree such that it maintains its balance? Well, I mean, this is in the class of, very leading questions that obviously, yes, there's an entire section on this in the textbook, which hopefully you have read, right? There's a class of transformations that we can perform on binary search trees where if we write some extra code, we can build intelligence into it to be able to see, oh, this addition is going to unbalance my tree. But if I move some nodes back and forth, I can rebalance this tree, or at least minimize the amount of unbalance, right? Cool stuff. If you didn't follow that, go back and read that section of the chapter again and see if it makes more sense now that we've been through the whole building of the binary search tree, all right? Because those kind of transformations are fair game for the final exam, all right? So make sure you understand why we are doing those transformations and how they maintain the balance of the tree. I don't have time to implement a whole bunch of it. The code's kind of hairy. But on paper diagrams, you ought to be able to look at an unbalanced one and figure out, if I add a new node to this, how do I restore the balance? Sorry, I said that wrong. Look at a balanced one where I add a new one that's going to make it unbalanced and figure out what are the transformations I need to do to get it to be balanced. That isn't just slurp everything out and rebuild it from scratch. All right? Okay. Other binary trees, or other trees, I guess I should say. We've got a bunch of different ways that we use tree data structures in addition to binary search trees. I guess I should bring my slides up here. So we will put this under the category of other tree variations. Nice long list in the textbook here, but I want to cover at least a few of them. So there are decision trees, which are actually an important part of data mining and artificial intelligence. So decision trees are trees where we encode information that we might have as a form. How many of you have played 20 questions at some point? Right? Everybody knows the game 20 questions. So, you know, I think of some totally random thing, and I challenge my children to ask me 20 yes or no questions, and they got to be precise about, you know, what kind of questions they're going to ask. And the goal is for them to figure out what this random thing is that we played this on the way to a restaurant the other day, and they were asking me 20 questions about what the restaurant was. And my son, bless his heart, finally devolved to, does the first letter of the restaurant's name occur in the first half of the he was going to do like a binary search of the alphabet to get the spelling of the name because he'd given up on the category part. But that's a great computer science algorithm, actually. So decision trees are basically an encoding of 20 questions. So, you know, I have a bunch of satellite data, for example, that I've taken of forests in a large state, and I want to try to identify the parts of the forest that are going to be susceptible to forest fire. So I've got some kind of model, and I've got a bunch of data from the satellite, and I want to do statistical analyses on this model to figure out what are the important parts of the data that I have. And so I might end up building some kind of decision tree where I can, through various artificial techniques, figure out, well, the most important question to ask is there greater than 50% of the trees that appear to be dead, right? So are there lots of dead trees? Dead trees, right? And if it's yes, then I go this way down the tree. And if it's no, well, then I've got another question over here that I want to ask, right? So we could have a whole bunch of different questions, yes, no questions, related to our data that help us to classify, you know, if I follow this path and this path down here, well, this gets me to forest fire, and that's bad, right? And I want to be able to use this decision tree to very quickly ask. We're basically automating the 20 questions game with the computer. So decision trees like this get built into all different kinds of expert systems where you're trying to encode human wisdom and experience into an algorithm that can very quickly arrive at a reasonable decision. All right, and that's based on the same kind of tree algorithms that we've already been talking about. And so we're really interested in the nodes and their children and the traversals that it takes to build this kind of tree. You can spend, you know, a couple weeks in an artificial intelligence class just talking about how decisions tree work. Another very common kind of tree is expression or parse trees. Can't type. So the last couple of years, Dr. Slattery has taught the compilers course here, but compilers is actually one of my favorite courses to teach. I haven't gotten to teach it the last couple cycles. But one of the things that I really like about teaching compilers is you get to see how programming languages really work underneath. And one of the essential data structures in compilers is this notion of expression tree, because different programming languages have different ways of spelling out operations, but a compiler is able to understand the sort of underlying structure of those operations and map it into machine language or machine code for the particular machine that we're on. And expression trees are a really important part of that. So, you know, for example, I could take the simple binary arithmetic expression 5 plus 6 times 7. And what is this equal to? 47, right? So we all know the rules of precedence that tell us that multiplication here is more important than addition. And even though we read the expression left to right, multiplication takes precedence. And so we do that operation first. Well, a computer doesn't know that unless we build into the programming language compiler rules for understanding those kinds of systems. And so an expression tree representation that a compiler used for this would be, well, I've got a multiply node up here, and its child on one side is the operand 7, and its child on the other side is the result of adding together the 5 and the 6. And that's what we call an expression tree. And you can build much bigger expression trees that represent your entire Java class and all of its methods and all of its data, right? And it's out of these expression trees that we then perform the additional stages that a compiler does to actually produce machine runnable code from a human readable programming language. So it's a really cool use of these tree data structures. Yeah, Nicholas.
Would that give you 77, or would you have to do the
Oh, I built the wrong expression tree, didn't I?
Yeah.
Thank you. Yes. Oh, this is why I'm not allowed to teach compilers anymore. Yeah. This is totally backwards, right? This is, if I parenthesize this expression, right, then it's not 47, it's 37. And this would be the correct expression tree for that. No, it's still not right. Oh, for heaven's sakes. What did I do here? No, that's not 37, right? It's 5 plus 6, 11, times 7, 77. Try that again. Does that run right? 77? We'll go with 77? Yeah, oh man. That's why I'm down here stuck in teaching data structures instead of compilers. But we can build the correct expression tree for the other version where multiplication takes precedence, right? That the multiply node would be down lower here. You'd have plus 5, and then its right-hand child, multiply 6 times 7, right? So expression trees are super important for understanding what the programming language really means, yeah? There's R trees, there's prefix trees, which we can use to encode different kinds of textual data. B trees are super important for any kind of database application. There's some nice diagrams of those in the textbook. You should at least take a look at those. It's unlikely you're going to get asked to write a B tree on the fly, but every computer scientist should at least know that B trees are a fundamental data structure that are related to the block size on hard disks. That's what makes them so great for databases, and that they're a critical part of how modern database architectures are so efficient. And they're basically a variation on our binary search tree where I'm allowed to have more than one piece of data in each child node, and I can have these links wherever I expand stuff. B trees are super cool, and we don't have time to talk about them in this course, other than to mention in passing. You should read that section of the textbook so that you'll understand them when you get to databases. AVL trees, red-black trees are all terms that you should at least have heard of, even if we're not going to spend time implementing in this particular class. All right? That concludes our tree chapter. So on Friday, we're going to do a little bit of GUI stuff, and then we'll start on the maps collection framework and hash codes. All right, good luck submitting your stuff tonight.